A very good morning to all of you. I welcome all of you to the fourth day of the workshop conducted by the Sri Lanka University Technical Officers Union. It's my pleasure to welcome our guest speaker for today, Professor Anchit W. Pallegama, Director, Center of Quality Assurance, University of Peradeniya, and Professor in Physiology, Department of Basic Sciences, Faculty of Dental Sciences, University of Peradeniya. Professor Pallegama obtained his bachelor's degree in Dental Sciences from the Faculty of Dental Sciences, University of Peradeniya in 1997, and a doctorate in 2005 from Tokyo Medicine and Dental University in Japan. He has served as the director of the Staff Development Center of University of Peradeniya from 2015 to 2020. During his 26-year academic stint at University of Peradeniya, Professor Pallegama has written books and book chapters in statistics and research methodology, been a recipient of presidential awards for his research. He has been teaching research methodology since 2008. 28 peer-reviewed journals and more than 70 presentations in local and international journals shows his research capabilities with the H index of 10. His main research interest in pain mechanisms. Professor Pallegama will enlighten our membership about technical officers' inputs into research activities. Thank you, and over to you, sir.
Thank you. Good morning to all of you. Can you hear me, Bill? One confirmation. Right. First, let me thank the Sri Lanka University's Technical Officers Union for inviting me to conduct this session. At the same time, as a senior academic in the country, I'm really glad that the university Technical Officers Union is organizing this kind of workshops for continuous professional development of their membership. So in today's session, my objective is to take you through a small journey in research and how, as technical officers of the university system, can contribute to research in the country, and how you can assist the country to go to a different level with new knowledge, with development of new knowledge and innovations. So with your permission, let me share my slides. Right. Thank you very much, and I'm sorry about the small delay I had. So this will be an introduction to research methodology. I'm pretty sure that some of you, or maybe almost all of you, have already got engaged in research. And I would like, if you can type in the chat box if you have already got involved in research, and if you have a publication to the credit of your name. When I mean a publication, it means a journal article. It's not an abstract. Can you just type yes in the chat box? Hope you got my question. Like it is those who have a research publication to your name. It is as a published journal article. Okay, right. Okay, there are a few. That's great, and those who have at least one or two publication or the presentation as an abstract in one of the research forum, just type only Y. Just type only Y. If you have contributed to any research, and if you have at least an abstract to your name, as maybe as the first author, second author, third author, fourth author, it's all right. If your name is there in an abstract, just type yes. Just type Y. All right, thank you very much. It seems a large majority of you have some exposure and experience in relation to research. And some exposure will help you to understand what I say. And don't think that I'm trying to talk some difficult stuff. I will try to keep it as simple as possible. And this one, we will try to understand the research philosophy and how to draw conclusions from finding of a research, and how designing and implementation work in research. And also, I will introduce you to internal and external validity, which is an important concept in research. So it's a simple but important concept in research. So that your contribution is really there in relation to research in preserving internal and external validity of research. And also how internal and external validity will jeopardized or will get lost. What kind of errors will contribute to loss of internal and external validity. I will take you through this, and we will discuss what research is and basic research types, basic elements of research, some conceptual understanding on the topic, and your contribution to research. And if I am too fast, please let me know. And also you are free to ask questions. And I heard that you have a kind of a guideline to ask questions on the chat box. That is all right. So please ask your questions. And of course, if your organizers permit, I don't mind even raising your voice and asking questions. And if you feel that if you are lost in the flow, and please let me know through the chat box. In simple words, research is actually a careful search for knowledge. A careful search for knowledge. Research is not actually an English term. Originally, it's Latin, French combination of meaning is there. And it means, the word research means a careful search of knowledge. Careful search for knowledge. And if I advance that meaning, I can say it as research is a meticulous and systematic inquiry. We inquire into a problem. Research is a meticulous and systematic inquiry to develop new knowledge by revising or discovering facts. Research can revise existing knowledge or can discover new knowledge and theories, and using this new knowledge, devising new applications or coming up with new innovations. And if I can break this into two, if necessary, actually it is the first part up to this point, developing new knowledge. And after that, using that knowledge to make innovations. So that is actually what we say as research. Research is mainly to develop new knowledge and come up with new innovations using that knowledge is development. So that is what we say as research and development. That is what we identify or say as research and development. Hope that you get this distinction clear. So, for example, those technical officers probably who are in engineering faculties, mainly perhaps, and even it can be true in other faculties like even agriculture faculty and many other faculty, even medical faculty, dental faculty. And if a researcher or if you use existing knowledge and try to come up with a new innovation. For example, you can recall the innovation at University of Peradeniya. Now, you know, there's a chemistry department with several colleagues, several researchers, develop a face mask. So they use existing knowledge in nanotechnology and many other technology, and they came up with this production. So that is an innovation, a development. But development or the finding of nanotechnology, that knowledge is an outcome of research mainly. So please keep this distinction, but broadly we can call both research. It's possible and people do it because without new knowledge, we can't come up with new products. And research can be categorized into mainly two types. And that is a major type of research is called a qualitative research, and another type of research is called quantitative research. And sorry, I was helping Mr. Prasad here a little bit. This qualitative research is mainly, it's mainly started in humanities, social sciences. They are not doing, or they are not dealing with numbers and measurements. I mean, measurements that we mean in sciences, right? We measure things in liters, milliliters, microliters, micrometers. We make large number of measurements in our research, or we gather data as numbers through questionnaires or Google Forms or whatever. We collect numbers most of the time as data. For some researchers who are doing a different type of research in the world, they don't collect data as numbers. They collect data as words or ideas, opinions. And there's another systematic way of going into these collected opinions. Now, for example, they will meet different participants, research participants. They will interview them. They will gather their ideas. They will note them down, or they might even video record them. And they will later use another methodology, another way, right? Another method to analyze, summarize, and generate some summary versions of those ideas or hypotheses. So they might even generate new hypotheses with the collections of those summary ideas. And they might even come up with some conclusions or some broader or overarching or like conceptual ideas or theories based on the ideas collected. So they don't use statistical software. They don't feed data into a statistical Excel sheet. No, there's another way of handling that kind of qualitative data. And such research is called qualitative research, qualitative data. That data is called qualitative data, and that type of research is called qualitative research. This happen mainly in humanities, social sciences. And I mean, it doesn't mean that it doesn't happen in other disciplines, but I know now in even health sciences, qualitative research is happening and it is used. Now it's getting popular actually, because we can get into certain problems or ideas through qualitative research rather than quantitative research. And also, perhaps if that research question or that research idea is totally new, it may be a little difficult for us to design a quantitative study to make very precise, careful, very clear and identified measurements. So rather, perhaps it would be better at first to do a small qualitative study and refine the research question, and then embark on a quantitative study. So in quantitative studies, we mainly collect data as numbers, percentages, decimals will get involved, and there will be at least a score. I would say score. There will be at least a score of something, number of people, number of events, percentages, or mean values, standard deviations. All these things will get involved in quantitative research. Nobody will find standard deviations or mean values or medians or such statistics in qualitative research. Those will not be available. We can't find a mean idea or average idea of some ideas. It's difficult. You get what I mean. So when we collect ideas or opinions of people, we can't calculate the average opinion. No. So, but we can summarize and we can have a summary view of ideas. So that is what happens in qualitative research. Hope this difference is clear. And from this point onward, I'm going to concentrate on quantitative research because I know as technical officers, most of the time you are attached to science-based faculties, and very rarely we find technical officers in the faculties of arts and other humanities and fine arts, etc. There are, especially ICT technical officers, etc. But it is less. I mean, we have large number of technical officers in science-based faculties, and usually these faculties mostly they are with quantitative research. So because this could be a different topic, so that needs a lot of other time for me to talk about qualitative research. So from this point onward, I concentrate only on quantitative research. Hope that is clear. Right. There are different ways of producing new knowledge in the world. There are different ways of producing new knowledge in the world. And there are, we know at least 8 different ways of producing new knowledge in the world. And study or learning about, no, forget about research, learning about new ways of producing research. And that subject is called actually epistemology. Epistemology. So that's a different subject. So in that, we know there are different ways of producing new knowledge. And for example, even knowledge produced by religious leaders. Let us take Lord Buddha or Jesus Christ or any other religious leader. I mean, they never cited anyone else. So they didn't say that this is in that book, so I am teaching it to you, or this is in that journal paper, I am teaching it to you. No, their knowledge, what they said is original. So that it is one way of producing knowledge to the world, these religious opinions or views of these religious leaders. Likewise, this our method of, I will come back to that in detail later, what is called scientific method is another one out of those methods to produce new knowledge to the world. An origin of this is actually in the history. You know, in the past, in Greek and all that, we had people called philosophers. We call them philosophers or darshanika, and but they were not like Lord Buddha and other people, the religious leaders. They had a systematic way of producing new knowledge. Philosophers had a method. The philosophers that was the method that was followed by philosophers is called deductive reasoning. Deductive reasoning. Now they start from a premise. Now, premise is an original existing statement or existing knowledge. So they work along these premises and produce or come up with new conclusions. Now, I can think about one example like this. Now, just imagine I'm a doctor looking at patients. And I know in this area, in this period, there is a flu infection going on. There is a flu. There's a flu. And I know that there is a flu. I know already it is common among children. It's spreading among children. That also I know. And that flu produced fever. Flu produced fever. That is also true. Now I have a child in the clinic with fever. Child with fever. Now, if I use my deductive thinking or deductive reasoning, or you can call it deductive thinking, there is a flu and it's common among children, and that flu produced fever. This statement is right. This is also right. It is known. Now it is published. It's on newspapers and we know. And it produced fever. That also we know. And now this is a child and he has fever as well. So that this child has flu. So I just come down thinking like that. I'm just thinking. I'm just thinking. I can take another example. I know smoking causes cancer. So let me put it as another example. Okay, smoking causes cancer, lung cancer. Smoking causes lung cancer. Now, I have Prasad with me, and Prasad is a smoker. So if this is true, smoking causes lung cancer is true. And Prasad is a smoker, that is also true in front of me, Prasad is smoking. Then what could be my conclusion? Okay, then Prasad get cancer. So this line of thinking is called deductive thinking. Deductive thinking. So that is how actually many Greek philosophers and other philosophers produce new knowledge. They concentrated on existing knowledge. And this is one premise. Smoking causes cancer. And the person is a smoker. So the person is going to get cancer. I mean, you can relate it to any environment. You can relate it to any incident in relation to your discipline. I mean, we use, to be honest, we use deductive thinking in our everyday life. We use our deductive thinking in our everyday life. The opposite of is the inductive thinking. Opposite of this is the inductive thinking. That's called inductive thinking. That is a bottom-up method. That is a bottom-up method. First, we concentrate on our observations. First, we concentrate on our observations. And we think of a pattern. And we generate a hypothesis. At least this inductive thinking, these 3 steps will be there. These 3 steps will be there. For example, just imagine I'm teaching in a class. I'm teaching in the classroom. When I ask a question, okay, when I ask the first question, a girl answered. A girl answered. So after some time, when I asked the second question, again, a girl answered. Then after some more time, I asked the third question, a boy answered. Fourth time, again a girl answered. Fifth time, again a girl answered. See, I know now, I observe, it was the girls. Actually, they were girls who answered my questions most of the time. So that is my observation. Whenever I ask a question, it's usually girls who answer questions or provide answers. So then I observe a kind of a pattern. And based on that pattern, I get into a conclusion that in this batch of students, I conclude that girls are more intelligent than boys. Girls are more intelligent than boys. This is my observation. Through my observation, I picked up a pattern. Because of that pattern, I came into some sort of a conclusion. I actually developed a hypothesis that girls, I thought that probably in this batch of students, girls are more intelligent than boys. Girls are more intelligent than boys. Can you like just tell me, answering in the chat box? Okay, someone has asked for the slides in my presentation. Yes, of course, I will share the PDF version of these slides with your union, so you can get a copy. So you don't worry about taking notes, just listen to carefully and interact with us, okay? So my question is, okay, now in this situation, my conclusion, girls are more intelligent than boys. Is it correct or wrong? Those who think that it is correct can type as C. Those who think that it is wrong can type as wrong, W. Those who think that this is correct can type as C. They can type as C. And those who think that it is wrong can type it as W. Okay, thank you. Right, thanks for the responses. Good, that your attempt is really appreciated. Good attempt. And let me get back. I had some observations. These are all observations. Anything I see, or anything that we hear, or anything that we taste, anything that we experience, all these are observations, right? So here I saw it, I heard it, both. Girls are answering. So far only one boy answered. So it was mostly girls. So observing this pattern, I concluded that girls probably in this batch. I concluded that probably in this batch, girls are more intelligent than boys. Why I said probably in this batch? Because it is a conclusion I arrived at with limited number of observations, so that if I do the same test in another class, I might experience the opposite result. Or if I get another class, I might experience again the same results. So my conclusion based on these limited numbers, that is why I said probably girls are more intelligent than boys, probably, until it is really measured in the class, either recruiting the entire class or a representative sample. We do not know whether this is true. Maybe for some reason, the smart boys kept silent when I was asking questions. So that is how an observation can go wrong. So still, I do not know whether it is true or false, and that is why it is called a hypothesis. That is why it is called a hypothesis. අපි hypothesis එකක් කියන්නේ ඒකයි. අපි තාම දන්නේ නැහැ ඒක හරියටම ඇත්තද බොරුද කියලා. So to decide that this is true, we need to design a formal experiment and run the experiment, and we have to come to a conclusion. Okay. Any questions or any issues so far? So inductive thinking or inductive reasoning can generate only hypothesis, or if when hypothesis is observed many times, it can be even considered as a theory. So the experimentation will result in theory. So is the difference clear? Is the difference clear? Right? In the deductive reasoning, we come down from a non-sentences, non-statements. We come down from non-statement. Okay. Now I can use even this non-statement I can convert it back to a deductive thinking. I can convert it back to deductive thinking. For example, now, if this, I can start saying, if this is true. Now, I said this is a hypothesis, it's a probability. It's probable. It's a hypothesis. Can be true, it may not be true. Okay, so let us move on to the next step. If this is true, that means if girls are more intelligent than boys, if I take all girls, to this side, all boys to this side, if I measure their intelligence level by IQ measuring system, a reliable IQ measuring system, and if I measure their intelligence by IQ measuring system, if I calculate the mean values for girls and mean values for boys, right? Let me go back. If this hypothesis is true, now let us recall, you look at this. Now, how this hypothesis was generated. I just observed when I was teaching, all my questions, except one, all my questions were answered by girls. So based on that pattern, I came to a decision that probably in this batch, girls are more intelligent than boys. I think we decide in this way, in an inductive manner, many times. Let me take another example. Now, when you drive, it happens to be a Saturday, you experience here a huge traffic. You don't experience that much of traffic on other days. And on next Saturday also experience a huge traffic. Subsequent Saturday also you experience a huge traffic. Now that is your observation. On Saturdays you experience a huge traffic. So now as a result you come into a conclusion, okay, I will not go to town on Saturdays. Saturday there is huge traffic. But it may not be true on the following Saturday. That's the thing. Inductive thinking may not be, the decisions that we take with inductive thinking will not be always true. But of course, we make such decisions many times. We in our daily life we use it. No, just you're sending your kids to tuition teachers, right? You're sending your kids to tuition masters. Now there's a tuition master who teaches maths, and a previous student has passed well after learning from him. Another student has passed the exam after learning from that teacher. And you get to know there's another student who has passed well after getting tuition from that teacher. Okay, now you decide that teacher is good. So what thinking is that? Inductive thinking or deductive thinking? Okay, just provide me an answer in the chat box. What thinking was that? Was it an inductive thinking or deductive thinking? You can just type IT or DT. Yes, great. That is inductive thinking. Okay, that's inductive thinking. Okay, now I'm running a small experiment, right? Okay, because of that, my conclusion, hypothesis that I have made, I'm really testing it. I'm sending my kid also to that teacher. So whether he will pass the exam or not pass the exam because of the help that we are getting from that teacher is the really the deductive, deductive part of it. So likewise, I mean, let me develop this example again. Because of my observation, I decided that girls are more intelligent than boys. So then I jump into the other side of it. Okay, if this hypothesis is true, that means if girls are more intelligent than boys, if this hypothesis is true, if I get all girls or a good sample of girls, and if I get a good sample of boys, and if I measure their intelligence level, if I calculate mean value of girls and mean value of boys, and what should be the big one? What should be the big one? Girls or boys? Just answer G or B. G or B. If this hypothesis is true, this mean value, girls' mean value on intelligence level should be bigger than boys. Now look at this. Deductively, we develop an hypothesis. And inductively, we develop an hypothesis. And deductively, we develop or design an experiment. Deductively, we develop or design an experiment. Now we have already designed an experiment. On my observation, I decided on a hypothesis. We use that hypothesis, and if this hypothesis is true, I'm going to get two sample of one sample of girls and one sample of boys, and I'm going to design a measurement. I decided a particular IQ questionnaire to measure the intelligence level, and I plan to calculate their mean values, and I plan to compare their mean values with a statistical test like t-test. So see what we have done. Using inductive thinking, we decide, well, we came up or we arrived at a hypothesis. Inductive reasoning वलिंग आती hypothesis का develop करा. Deductive reasoning वलिंग अभी experimental design करा. So what we are really doing in science in research is using these two original, very old two thinking processes in scientific method. We use inductive reasoning to come up with a hypothesis. We use deductive reasoning to design an experiment. Right. Now, once I design this experiment, it's a simple thing to execute it. Hypothesis generation has happened. Experiment designing has happened. Now I ask Prasad, okay, go and find a representative sample of girls and go and find a representative sample of boys. Here is the questionnaire. Use that questionnaire. Administer this questionnaire to this sample of girls and this sample of boys. Calculate values. Calculate mean values. Use a t-test, statistical software, compare the mean values, come to the conclusion. Now, if the t-test later on decides, if the t-test later on decide that mean girls is really bigger than mean boys, if the statistical test, after really running the experiment, now we select samples, we make measurements, we calculate mean values, X bar girls and X bar boys, and we compare these mean values using a t-test. Now that means, you see, there are three steps. Inductively, we came at the hypothesis. Deductively, we designed the experiment, and now we are executing the experiment, design experiment. We are executing the design experiment. So in the execution, at the end, if statistical software decides that mean value of girls is really significantly bigger than mean value of boys, I can conclude confidently that my hypothesis was true. My hypothesis has been true. So from that point onward, it is not a hypothesis, it is a fact. It is a truth. So hope this bit is clear to you. So based on this knowledge, actually, this is the research process. Inductively, we come at hypothesis. Deductively, we design the experiment. For the prediction, we call it prediction. Prediction, now initial prediction that we decided. If this hypothesis is true, if girls are more intelligent than boys, my prediction is through inductive thinking, mean value of girls should be bigger than mean value of boys. So this is the hypothesis that we arrived at through inductive thinking, and this is the prediction that we arrived through deductive thinking. Now this prediction is really tested in really implementing the experiment. This is really the doing part. This is what happens in the laboratory. This is what happened in the maybe that happens in the field. Maybe this happens in the computers. Maybe this happens in another setting, clinic, hospital, wherever this research really execution happens, we call it research setting. Research setting. That location is the research setting. Maybe it's just happened in the in petri dishes in a laboratory. Execution. So if I ask you an important question, so in that case, the most important part of the research, of any research, happens where? Just provide me your answer in the chat box. The most important part of a research happens where? What is the location? The most important part of a research happens where? I will give you 1 minute and think. Hello, any answers? Any answers? So research if I correct it again, this is the research setting where the implementation happens. It can be a clinic, it can be the field, it can be it can be in under the sea, or it can be on the sky, or wherever our sample is there. That is the research setting. Okay, that happens there. So, what is the location of the most important part of a research? That is my question. Okay, now Professor Mr. Prasad and your union is ready to give you a gift. I use this question for that. Okay, what is the location of the research, the most important part of the research, or the getting a lot of answers? So I'm asking, okay, shall I give the question from the beginning? Right, I'm thinking of a place now. I'm thinking of a place. Now, implementation happens in the research setting. My question is, what is the most, for the place that the most important part of the research happens? Or where does the most important part of the research occur or happens? Okay, right. I still didn't get, some people are getting somewhat little close, but didn't get the correct answer. Now, if you look at the sample collection, where does it happen? It's happened here. It's happened here. When to implement, only we collect. Now we collect sample of boys and sample of girls. Right? Okay. So let me provide the answer then. Didn't receive an answer. And if there is any problem in this part, will the research work? It will not work. If there is any issue in this part, will it work? It will not work. So that means we come up with the wrong design. I mean, here we come up with the hypothesis. Here we come up with the design. Right? Okay, I will give you 30 seconds. Okay. Right. So some people are right. Induction, hypothesis, deduction. Okay. One person gave that area, induction, hypothesis, deduction. But where does it happen? What is the location? Now we implement the research in the research setting, maybe laboratory or somewhere. So where does this happen? Any ideas? It's in your head. It's in your head. So most important part of the research happens in the head. Because if you go wrong here, anywhere, and you ask for even a billion research grant, and you execute something which is a stupid research. If you make a mistake in the generation of hypothesis, or if you make a mistake in the deduction, that is you're deciding or designing your research, and after having a wrong design, and you get a grant from WHO, 40 million, 50 million, 200 million, 400 million, and you run a useless research project. You implement a useless research. So, masterpiece of research is this piece that happens in the head. So I can easily ask now, for example, I know most of our technical officers are involved in this part of research. Once this has happened, it's a simple implementation. And if you are good at measuring, if you are good at using a particular equipment or device, I mean, you will generate data, and someone will later, and this part you will generate data, here you will analyze data, and at this point, you conclude with statistical test. And all these things are mechanical steps. All these steps are very mechanical steps. The most useful for the real brilliant part of research is this part. So if this is not properly happened, if this has not properly happened, no point, actually this will be a waste. This will simply be a waste. I hope you got it. Actually, if I say, the person who do this part, the person who is engaged in this part is the researcher. The person who is doing this part is the RA, research assistant. Hope I made that difference. Hope that is clear. Of course, researcher can also get involved here, but I mean, you can leave it to a research assistant, no problem. Once you design it well, and I mean, if you have a careful research assistant, he will execute your design. He will execute your design, that is your protocol that you design here, without a mistake. But I mean, that depends on his experience, the quality of equipment that you have and all that, that's true. But the brilliant part of research is this part. Right. So with that, let me, all I have discussed this. So here, you know, probably you have seen this, at least you have seen animations of similar animations of this device. This is called the hourglass. Good old days, people have used similar devices to measure time. So when all sand go down, they turn it upside down and leave it again, and that is counted as another hour. The time taken for the sand to go down to the other chamber is taken as 1 hour. So that was an original measurement. So why I use this here? We already have a huge knowledge base. We already have a huge knowledge base. if you look at anything, we know a lot now. It's not like the time of Archimedes, so not like the time of Alexander Graham Bell or those people who did basic inventions. We know a lot now. It's really difficult to do research. Why? We know a lot already. Already a lot of knowledge is found. It doesn't mean that everything is found. We have gaps. We have a lot of unknown areas. Now look at CKDU, chronic kidney disease of unknown origin. We don't know the reason. Look at COVID-19. Scientists took at least some time to identify the virus and also to give it a name. They took some more time, several weeks actually. But still there's a lot of gray areas. There are a lot of gray areas. We do not know. Now, a lot of research is happening now on COVID. Now, what happened? For example, let us take COVID. Now, already at the beginning, nobody knew about nothing about it was zero. But now just imagine you are going to do a research on COVID. We know a lot about COVID. But still, there are areas that we do not know. So we pick one of these areas. And refine it. And that becomes the new research question. And when we design the new research and execute that new research, and when we find that answer to that research question, what we have done is we have added that new information to the knowledge base, and we have expanded the knowledge based on COVID. So research is like that. Already there is a huge knowledge base, but there are gaps, and you pick a gap, and that gap is known as the research question, a question to which the answer is not known. The question to which the answer is not known to us yet. And to find the answer to that research question, we design the research using our deductive thinking. Now, this could be a hypothesis. Research question is a hypothesis. And on that hypothesis, we deductively design the research. When you find the answer to that research question, now we are expanding the knowledge base on COVID. That is the idea. We expanded the knowledge base on COVID. And so here I will try to give it as a flowchart. Now, initially we ask a question. How do we ask a question? We ask the question through our inductive thinking. I observe, then I saw girls were answering more than boys. So then my question was whether girls of this batch of students are more intelligent than boys. That was my research question. Or if I put it in without a question form, if I put it as a statement, girls are more intelligent than boys. And that is called hypothesis. If I ask it as a question, whether girls are more intelligent than boys, that is called research question. That's a question. It is only the way we write it. So any hypothesis can be converted to a research question, or any research question can be, almost all research questions except these qualitative research questions can be written as a hypothesis. Hope I made that clear. So when we have a research question, we need to do a lot of background data finding research, and we need to read a lot. We need to, let us get back to this one. Why? We already know a lot. On that topic. So when we pick a research question, if I do not know that it is not known area, or if I think, maybe I'm an inexperienced researcher or research student, I'm talking out of my own experience. So I think that, okay, this is good to ask. I have seen the same thing from my research students, undergraduate students especially. They think, okay, let us find this. For example, very recently, a research student from another faculty, supervised by another senior academic staff member, came to me knowing that I'm good in statistics to get the data analyzed. Actually, supervisor is also a non-expert in the subject, not an expert in that subject, unfortunately, because it is a new faculty and students are supervised by academics of other faculties, so that they are probably the supervisor is not the expert in the subject. That happens, unfortunately. So the research question of that student has been to know whether eating sugar causes dental caries. That has been the research question. And they have already done the research and they have gathered the data as well. And they came to me, the student came to me to get the data analyzed. So I had to explain it to the student. Unfortunately, that this fact is at least 150 years old. We knew that eating sugar causes dental caries at least before 100 years. So it is already a known fact. But if I do not, when I get a research question, if I go into this literature and really review the literature, read literature and find out, doing internet search and all that, I might think that it is a new question. But if you do a good literature review, only we realize that the research has already happened. And we even know the answer to the question. And so that based on that, we can refine the research question. Based on the literature review, we can refine the research question and the hypothesis. Okay, now, if that student, let us take that same student. If that student read it, probably he or she will find that already that is known. Okay, eating sugar causes dental caries. But I mean, if she goes into more and more information, literature, and it may not be clear, perhaps, sugar in the liquid form, sugar as a liquid. Now we drink food drinks, soft drinks, etc. Now sugar, a lot of sugar. I mean, if you take Coca-Cola and all, lots of sugar. And sugar as a solid form, whether which form of sugar cause more caries could have been a new question. Then you see the research question get modified. When you do a lot of good literature review, the research question get modified and the hypothesis get modified. So as a result, the hypothesis would have been there is a difference in eating sugar in solid or liquid form in relation to causing dental caries. Or when I do a lot of research, if I find out probably there's a chance now after when I go through a lot of literature, I think now probably eating sugar in solid form has a higher chance of giving rise to caries. Then in that case, I can write the hypothesis, the one-way hypothesis. Eating sugar in solid form causes more dental caries than sugar in liquid form. Likewise, our girls are more intelligent than boys. So that is a kind of a one-way hypothesis. Or I mean, if you are not sure about the direction, whether solid form causes more caries or liquid form causes more caries, we can ask a question whether there is any difference in the influence of eating sugar as solid form or liquid form in relation to posing dental caries. So, however, you see, unless you do a good literature search, we will make a mistake in our research question and hypothesis that cannot be corrected later. So they will even collect the data, they will analyze and try to publish. And then when they send it to a journal, the reviewers will say, this is a bullshit research and this has happened. This we already know. There's no point of you doing this research. There's nothing new. The reviewers will say, there's nothing new in this research, so that we don't want to publish it. So, I mean, I experienced the same thing. I was in another research forum one day. A researcher had done a research on rats. Researcher had done a research on rats, guinea pigs actually. And the researcher was a professor from another discipline actually. The researcher was presenting data in a research session. In a symposium, researcher was presenting, making an oral presentation, and that professor was presenting data. After the presentation time, when the question and answer time came, discussion time, within the discussion time, there was another professor was telling everybody, now this research has done on human beings many times before, and we know the answer, and there's no point in doing this research on rat now. You understand? If that researcher has gone through the literature well, he would have realized that this research already done on human, even non-human beings, and the answer is no. So that is why anybody who get a basic research question, should do a very thorough background literature search, should read into the literature, and then finalize the hypothesis. And then deductively, that means you inductively develop hypothesis, deductively develop experiment, and then you run the experiment, third phase, and then you analyze the results. When you analyze the results, the statistical test will tell you whether your hypothesis is true or whether hypothesis is false. Both are possible. And many times when you analyze data, we realize that the hypothesis, hypothesis it's not rejected by statistical test. So that means our hypothesis, our indication is probably that hypothesis is false. But if you are a very experienced researcher, you are still sure that this hypothesis should be true. Although your experiment says that hypothesis is false, you still feel that hypothesis is true. This should be true. Something probably went wrong in the experiment. So it's possible. Now, that is something that we are going to discuss later. What things can go wrong in an experiment? What things can go wrong in an experiment? Because now you have a good deductive thinking and generate a valid hypothesis. Imagine. Now, concentrate on this. You have a good deductive thinking and generate a good hypothesis. And you have, you have very good inductive thinking and generate a good hypothesis. I made a mistake. You have a good inductive thinking and generate a good hypothesis. And you use your deductive thinking and make a very good design. The design is perfect now. You have a very good design. And now you give it to a research assistant to implement it, execute it. And if the research assistant is not a careful person, he can easily make a mistake, or he can easily ignore a step. He can easily probably, now just imagine, now the researcher decides to make a particular measurement. And that device, that instrument that is capable of measuring that to the precision which is wanted by the researcher is not available in your lab. Just imagine that it is the researcher want to use a digital vernier caliper to make the measurement. That is in his design now. His idea is to measure the length with a digital vernier size width of that something of your sample with a digital vernier caliper, very high precision vernier caliper. Now with that design, the researcher gives it to you. You're the research assistant. And that vernier caliper, the researcher tell you, that the person who designed tell you that that vernier caliper is not available in your lab. It is available in another university or another laboratory. The researcher has already communicated with that head of a department or somebody to borrow that vernier caliper. So you are asked to go there, bring it and make the measurements. So just imagine that now you feel lazy. You feel lazy to go there, borrow it, and you borrow another less precise vernier caliper from another neighboring lab. And you make the measurements with that one. So that less precise vernier caliper will introduce more error to your data. So that the statistical analysis will come as the hypothesis is false. The researcher doesn't know that he start worrying. No, he believes that it should be true. So likewise, things can go wrong anywhere. And perhaps, just imagine now, the data is collected, data is given to a statistician to be analyzed. Statistician pick a wrong test, not the best statistical test for that data. Again, it will come as false. So when during implementation, research can go wrong anywhere. During implementation, research can go wrong anywhere. And what you want to find, you will not find. So that is why then when that happens, it is possible and it is necessary, you refine your methodology protocol again. And you can even refine your hypothesis if necessary. And you repeat it. You repeat it. And you can even repeat the same thing just to confirm the results. Just to confirm the results. Now, for example, a good question would be, smoking causing lung cancer. Smoking causing lung cancer. And if there are staff members here listening to me who are perhaps older than me, you may remember when we were kids, what was the advice on cigarette packets? What was the advice on cigarette packets? Was there any advice in relation to cancer? Was there any advice in relation to cancer on the cigarette packets? Actually, there wasn't. On the earliest warning that came, that said, Dumbima hanikara vimata pilivana. If you remember that, you will recall it. It was the only advice that was there. Dumbima hanikara vimata pilivana. So smoking can be harmful. That was just. Then some more research happened. People were thinking now, people were realizing that smoking causes lung cancer. Then later this advice changed. It changed gradually actually. Then later again, Dumbima pilika atikimata puluvana. Smoking can cause cancer. Smoking may cause cancer. Then it became smoking causes cancer. Then it became smoking causes lung cancer. And now you see, a cigarette packet is full of cancer images, etc. And now it is a strong message. Why? After 25 years, 30 years now, the same experiment, same hypothesis has been tested many thousand times. The hypothesis that smoking causes cancer has been tested by different researchers in the world in different labs, different settings. Some clinical setting, laboratory settings, and all that has been tested 1,000 times, 10,000 times, and the finding has been very clean and clear. And now it is a very clear message that smoking causes lung cancer and other cancers. So, I mean, it is possible that research happens repeatedly on the same hypothesis until we are very clear about the findings. So then it becomes, when that happens, like actually, when the same research, it is the same method, when the same research with a lot of refinements, with same hypothesis, slightly altered hypothesis, slightly different hypothesis being tested many times, ultimately it produces a theory, or it becomes almost a law. So it doesn't fail. So it becomes almost a law or theory or a fact. Now, smoking causing lung cancer is a fact because we know it. We know through 10,000s of experiments in different settings, done on animals, done on humans, done on patients, many experiments have proved smoking causes lung cancer. Now, if you look at now the present situation, now there are experiments. Researchers say that use of mobile phones causes brain cancer. Still, I do not know. There are research. At the same time, some researchers say it's not. It is not. But that is the present situation. So we don't get any advice on the mobile phone, on the back of the mobile phone, that more use of this device cause brain cancer. No indication like that. But maybe after 10 years to 15 years, if research proves, at least to a certain extent, that use of mobile device causes brain cancer, maybe there is an advice. One day there will be an advice printed on the back of a mobile phone. So it's a possibility. So knowledge should build up. Repeating the same hypothesis, testing the same hypothesis over and over again, many times, so that we get to know the truth in relation to the research question. So in that case, it is a potential research question, whether use of mobile phone causes brain cancer, whether use of mobile phones causes brain cancer. So in that case, if I write it as a hypothesis, the hypothesis would be use of mobile phones cause brain cancer. So that's the idea. Right, any questions so far? Any issues? Right? Okay, so then I think I'm informed to give you a small break, perhaps about 10 to 15 minutes. At the same time, I want all of you to write an example for inductive thinking. And write an example for inductive thinking and post it on the chat box. And as far as I heard, the first person who posts the correct flow, it will have 2-3 steps, right? So likewise, I observed more, I ask questions, more girls answer. So I assume that girls are more intelligent than boys. So there are 3 steps, at least there will be 3 steps for one inductive thinking. So I want you to write an example for inductive thinking, and the person who write the correct example, the first person who write the correct example will get a small gift from your union. So that is a small announcement. During the tea break, you can try it and you can post it. So I will decide whether it is correct or not, and I will inform your union about the person who posted the first correct answer. So in the meantime, we can get a quick break and we will start at 10:40. Okay, we will join back. I mean, you can stay join. Session will not be closed, we will come back at 10:40. Yes, thank you.
Now we will be starting second part of the session after 15 minutes. Thank you. I would like to cordially invite Professor Ranjit W. Pallegama to start second part of the session.
Right. Thanks. Welcome back. Can you hear me? All right. Okay. So as we discussed before, I know some of you are trying to answer. I just to help you again. It's what we need is an example for inductive thinking, but not for deductive thinking. So inductive thinking should ultimately result with the hypothesis. Right. So we observe a problem somewhere inductively. We observe a problem somewhere inductively. We then arrive at the research question, and we can convert it to even to a hypothesis. So I'm not going to talk a lot about that, but for statistical thinking, we convert even into another. We write it in another way, which is called a null hypothesis. So this is some statistical things that happens at the time of designing. But what we need to concentrate is the research questions or the hypothesis. When we generate a research question, now I can, for example, when we, I got to know from one of my colleague that there has been a patient in a clinic who used to eat the substance called babul. And later the patient is found to have cancer in the oral cavity. And a few weeks later, another patient was found to have, found to eat babul and found to have a cancer. And another couple of weeks later, the same doctor observed that another patient had a cancer and he also had a history of eating babul. So now you look at that doctor's mind, observing the same thing inductively and generating a hypothesis. Now that doctor's hypothesis that eating babul cause oral cancer. Eating babul cause oral cancer. So that now he has developed a hypothesis. But hypothesis is a probability. It may be true or may not be true unless it is tested experimentally and either proved or disproved. So for that, in designing, we can take a sample of people who eat babul, and we can take a sample of people who do not eat babul. We can observe them for 10 years and decide, now they are eating babul, no babul. After 10 years, we can decide, so those people who are eating babul, some people get cancer. Those who do not eat babul, only 1 or 2 get cancer. Maybe 0.01%. I mean, here maybe 2%. So statistics will decide that it is a significant difference and decide that eating babul cause cancer, perhaps. So likewise, once a hypothesis is generated, we test this in a sample of people. We got a sample of people eating babul, and sample of people who are not eating babul, and we observed them for 10 years. That's the research that we did. And that was the design. So that if eating babul is, doctor decided that hypothesis, babul causes cancer. Eating babul or no babul. So eating babul, people who eat babul get more cancer. So that that was the hypothesis. That was the hypothesis. So having that hypothesis, the experiment was designed deductively. So if we take a sample of people with babul, eating babul, sample who do not eat babul, and if we observe them to the future for 10 years, we should see more people eating babul developing cancer. That is the design. Now the experimenter really did it. After designing that, okay, in the clinic, they found a sample with sample of people who eat babul, and they found a sample of people who do not eat babul. They observe it for 10 years and found that 2% of people who eat babul develop cancer, but only 0.01% of people who do not eat babul develop cancer. So that proves the hypothesis. So likewise, when we generate a hypothesis and we design the experiment to be conducting a sample of the population. The population is the all people. Population is the whole. People who eat and people who do not eat babul. All right. But we cannot do this test in the entire world among all these people who eat babul and who do not eat babul. We can't do quantitative research like that. Usually we select a representative sample from the target population. So here the target population is, and we take a target population, a sample of people who are eating babul, sample of people who are not eating babul. And we compare them, and then we come to the conclusion with our research, and we infer findings, or we generalize findings to the population. So if I say it again, in the sample, if I observe that eating babul, people who eat babul develop more cancer compared to no babul people, I have done this experiment only in a sample. I have observed only 20 people who eat babul and 20 people who do not eat babul. So that there's no mistake in the sample. Those people who have been eating babul, 20 people. These people, 20 people who have not been eating babul. And I have observed them for 2 years, and I realized that 2% of them develop cancer, only 1.1% of them develop cancer. So this is statistically proved that eating babul causes cancer. So this entire experiment happened in a sample, but we generalized the findings to the population. So our conclusion of this research is that if you eat babul, this is in relation to the people in the population. If you eat babul, there is a chance that you get cancer, or eating babul can cause cancer. We can ask people then, after this experiment, we can ask people, okay, don't eat babul. If you eat babul, you can get cancer. So it's like that. So usually an experiment happens in a sample of the population. We can't recruit all people to a research. It is practically difficult. And it is more expensive as well. Now, if you want to do a research about smoking, again, now you look at the number of people who smoke in the society, huge, thousands. And the number of people who do not eat, again, thousands, 10,000, millions perhaps. So in that case, we can't do research recruiting all people who smoke. This is practically difficult. So we always do research in a sample. That is why sampling is necessary. And that is why a sample should be a representative sample. For example, if you make a mistake in sampling, if your research assistant had included people who do not eat babul into babul group, or people who eat babul into no babul group, the result will be wrong. The result will be wrong. So we have to be very careful in sampling. And also the sample size, that is also a matter. So all these issues are there in relation to sampling, and this is a little bit of statistics is also involved. And I really invite, as technical officers, it's really, really great if you can learn a little bit of statistics. If you can learn a little bit of statistics, because you are good in computer science, you are good with computers, you know how to use computers. So install a statistical software into your computer and start learning little by little. In that way, you can really help your research group, your professors or senior lecturers or senior researchers, and they will really value your contribution, and that will be really, really necessary. And so far we were discussing the research method or scientific method, right? And let us quickly look at different research types. I mean, there are two basic types. One thing is experimental research. Experimental research, you do something to the participant. You intervene. You manipulate something. So it will be an experimental research. So when we say experimental research, its idea is not that it happens only in a laboratory. Experimental research can happen in any setting. For example, if I take two groups of people, and if I ask them to eat babul, I ask them to eat babul, and I ask them not to eat babul. So I am giving them babul, right? So I am eating, I'm intervening them. I'm intervening them. So it's an experimental study. It's going to be an experimental study. So on the other hand, if I just find a group of people who eat babul, I'm not asking them to eat, but I'm just finding a group of people who eat babul, and I'm just finding a group of people who do not eat babul. I have not done anything to them. So it is just an observational study. So this is the basic division of research. I mean, this is true for almost all research actually. It's true for, I mean, you can do an experimental research with bacteria. You can do an observational research with bacteria. That is also possible. It doesn't only have to be human beings. You can do an interventional or experimental study with dogs or cats or rats or guinea pigs. And at the same time, you can do an observational study with guinea pigs. It doesn't, it's not based on the model, animal model or human model. It just, whether you intervene or whether you do not intervene. If you intervene, if you do something to them, if you give them a drug, if you give them a chemical, or just imagine now you take two groups of rats and keep one group under light, under bulb, and you keep the other group in a dark room. Have you intervened them? Is there any intervention? Yes. What is the intervention? Keeping them under light or keeping them in a dark room. So exposing them to light or not exposing them to light. That is the intervention. So it becomes an experimental study. And after that, actually, these can be divided into other subcategories like analytical or descriptive. I'm not going to really go into that details. And this can be divided into further subgroups like, I will show you this observational study, experimental study can be subdivided into different subtypes. Under observation, it can be explanatory study, it can be descriptive study, it can be analytical study, or depending on the time, it can be retrospective study or a cross-sectional study or a prospective study. I'm really not going into detail, right? So please, it depends on the research question. I mean, the research question will decide the research type, and also the research problem and the nature of the research problem will decide the research design, and also your available facilities, time availability, everything will decide the research type. This will depend on many factors. So when you think deductively, when you design your research, all this will be a matter, or it will be all these will be factors, so that you will pick a particular design which is appropriate to the research question. So the research design should be appropriate to the research question. And I'm not really going into detail. And let me look at the most important thing here. Now we do a research in a sample of subjects, maybe sample of rats or sample of bacteria, sample of human beings. So that is the findings in the study. But we do the research, or we get the findings in the study to get an idea about what is going on in the universe, or the nature, in the truth, or truth in the universe. We are studying bacteria to understand in a petri dish, in the laboratory, to understand what is really going on in relation to that bacteria in the nature. We are studying a sample of rats or guinea pigs in the laboratory within keeping them in a cage. And with that findings of the study, we can understand what is going on really in the nature. That is the idea. So whatever the findings in the study, we should be able to extrapolate or generalize, or we should be able to infer what is going on in the nature. That is the idea. So we should do this research in such a way that this inferring or generalization is possible. Generalization is possible. I will look at a couple of examples. Now, findings of the study should be inferred or should speak for the truth in the nature. Should speak for the truth in the nature. We should be able to interpret what is going on in the nature or in the society or in the environment in relation to our findings in the study. It is in general. So in that case, sample should be representative of the population. Now we have some idea. Now just imagine, I want to see whether now based on my hypothesis, I have predicted that girls are more intelligent than boys. When I do my research, I take the sample from engineering faculty. I take sample of boys from engineering faculty and sample of girls from engineering faculty. Or if I get a sample of boys from engineering faculty and sample of girls from arts faculty, and I do the research, will I really find the truth in the population? No, I will not, because my sample selection is a bias selection. So my samples are not representative of the population. Ideally, I should be taking few boys from engineering faculty, few boys from medical faculty, few boys from dental faculty, few boys from art faculty, and the same number of girls from all faculties, and measuring their intelligence level and comparing it to be a representative sample. So it is very important that we have to get a representative sample. And the measurement. And the measurement should speak for the real characteristics of the problem or that is phenomenon of interest. Now just imagine, now we are thinking of the intelligence level of boys and girls. Let us look at the same research problem. So what should be the measurement that I should use? Now my interest is understanding the intelligence level. But in measuring the level of intelligence, there are some standard ways. There are better ways, there are less accurate ways. Just imagine that I utilize a less accurate way of answering the intelligence or measuring the intelligence. Now I think, okay, I decide the small questionnaire. I design a small questionnaire and I give that questionnaire to, I design a questionnaire and I give that questionnaire to the sample of boys and girls and I measure their intelligence level. Is there a guarantee that my questionnaire will measure their intelligence level accurately? Or what would be the best? To get the best possible tool already available in the world to measure the intelligence level. So if I design my own questionnaire to measure the intelligence level, which is not tested and which is not proved to be correct or accurate, I might end up with another result. I might even not really measure intelligence level. I might measure something else. For example, if I design a questionnaire, I might perhaps measure their knowledge, not the intelligence level. So then whatever the readings that I get from my questionnaire is not the intelligence level, but it is knowledge about something. So that is a different reading. So it is very important that when we do research, now even the previous example, even using a high precision vernier caliper and less precision vernier caliper will give into different results. Will measure the characteristics in a different accuracy. So measurement should speak for the real characteristics. First thing, the measurement should be valid. Now, for example, a real example that I experienced, a researcher wanted to find out whether academic stress among first-year students, second-year students, third-year student, fourth-year student changes, whether it changed from the first year to the second year. It's a good question, no? Good research question. Whether the academic stress means the stress level that the students are having in relation to their academic program. Whether the academic stress level changes different from first year to final year. That was the research question. Okay, now the deductive lit was designed and samples were selected from every batch, and the stress level has been measured with a stress questionnaire. Stress level has been measured with a stress measuring questionnaire. And the researchers did not find any difference again. But they expected actually, and even I expect that perhaps the academic stress would be different in different batches, from first year to final year. Then they went back and analyzed what has happened. You know what has happened? The questionnaire that they had used is a stress measuring questionnaire, but it measures not only academic stress, that also measures other life stresses. For example, not having enough money. Students with problems with their parents. Students with problems with their families. Students with problems with their friends. Students with problems with their girlfriends, boyfriends. All can be stressful, right? And when that get added to stress measurement, now what the researchers have measured is not only the academic stress. What they have measured is the total stress level. So perhaps it is not different among batches. So it is really, really important when we decide on a research, and we need to decide whether the measurement we are making is really speaking for the characteristic that we want to measure. Otherwise, we can't generalize the findings. Otherwise, we can't. It's like selecting a bias sample. The other thing is the setting, the research setting, because we want to find out the problem in the real world. But unfortunately, we have to do the research in a particular setting. We have to do the research in a particular setting. So if the setting, now for example, the behavior of animals, now you want to study something in relation to the behavior of rats, right? But when you study the animals in the laboratory, keeping them in a cage, can we think that their behavior is similar to their natural behavior in the environment? No, it is very different. It's very distant. So that we need to select our research setting. For example, if you really want to study the behavior of animal, best thing is go to the jungle, videograph them when they are behaving in the natural environment, and study that. That should be the setting there. Not bringing them animal into the laboratory and studying them in the laboratory. Okay, studying them in the laboratory will be the ideal setting for another research question. For example, if you want to measure their anatomy or the body size or something, perhaps that will be all right. But if you want to study even their biochemical pathways, so how their brain work, again, if you can try to do it in the laboratory, but how their brain work will be different in the laboratory setting compared to their real natural when they behave in the natural environment. That is why actually now we have less value in research which are done in settings which are remote or distant from the natural setting. And that is one reason why researchers try their best to do the research in a setting which is close to the natural problem. So that is one thing that you need to keep in your mind. The other thing is the time. Time of research and the time that you're going to generalize. Now, for example, if we do research today in these days, those findings could be valid for next decade or next 10 years. And that is why even when we do research, we do not ask research students to go for literature that have been published 20 years or before. Because those findings may not be valid for today. And it can be true for many, many disciplines. So time is another factor in relation to generalizability. So for our findings of the study to be true, and for the finding of the study to, or the study to speak for the real problem in the nature, I mean, we should be able to generalize findings in relation to many of these. And the last one in relation to that is statistical model. So the statistical model should be a model that will really pick the relationship that we are trying to study. If we use a strong, wrong, or irrelevant, or less relevant statistical model, that might not pick the relationship that we are going to study, or that might not pick the real relationship that is there in the nature. So we cannot go wrong in relation to any of these things in designing the study, so that if we go wrong, whatever the findings that we get in our research, or the truth that we find in the research, that we have designed can be far away or distant from the truth in the reality. So we have to make sure that we don't make mistakes, or we are trying to have the best possible research design. So in relation to generalizing, I mean, it is, I told you, we discussed that it happens in a sample, and the sample and all these the aspects that should be there to for our generalization to work. Or if these are not there, we can't reliably generalize findings of our research to the population. That's the idea. So that is the basics of generalization. But we agree that we study the problem in a sample, so that our experiment that is done in the sample should be able to capture the problem in the population. Our experimental design that we do in the sample should be able to capture the problem in the population. Otherwise, we can't generalize. That is the idea. So it is true in relation to all these aspects that we discussed before. And sample is always a subset of the population. Don't worry about it. It has to be a representative. I mean, a sample is a subset. Now, if I take now, just imagine it's like this. I have a batch of 100 students. It has 60 girls and 40 boys. It has 60 girls and 40 boys. And if I take 10 boys, is it a sample? You can answer yes or no. If I take 10 boys, now this is the population. This is the population, 100 students with 60 girls and 40 boys. If I take 10 boys, is it a sample? That is my question. Okay. All right. Hope you can see me and you can hear me and you can see my slide as well, right? Yeah. Mama. Sorry. Hope you can hear me. All right. Okay, so let us continue. And I'm sorry about the disturbance that occurred. There was a power failure. And we were talking about the population as sample. And this is a very common place to make a mistake, and we do a wrong research. And if you do such a wrong research, by sample selection or and not representative sample, if we recruit a not representative sample, we will never be able to generalize our findings of our research to the population. And these are the things that we need to ensure to maintain generalizability of a research, So I took a quick, let me take a simple example. It's mainly in relation to qualitative or quantitative research, whatever the type of measurement that we take. And we have to ensure that we are measuring what we really want to measure. And also we are selecting the real most appropriate scale of measurement. And also there's another thing, we have to ensure accuracy and precision of a measurement. If time permits, I will talk about accuracy and precision later. And generalizability from measurement to the phenomenon. That means our measurement should speak for the real phenomenon. We should measure the real phenomenon in relation to the research question. These are the things that we need to ensure. And also in relation to the research setting, we need to make sure that our setting is as close as possible to the problem in nature. Our setting as close as much as possible to the problem in nature. That is why now when we do a drug test or drug trial, initially we do it, we might test it in petri dishes in the lab, or development can happen at that level. So we might do it on animal, test it on animal. We might even test it on even a small group of people. And then we test it on a larger group of people. And then we collect data in relation to the use of drug in the real population. So after that only we rely on research, because otherwise we really do not know how a drug will behave in the population. For example, this is true in relation to these COVID vaccines. We don't have that kind of real data in relation to the use, and now only we are collecting that kind of data, and then only we can really decide on what will happen, what will be the complication, what will be the consequences, what will be the real effectiveness, long-term effectiveness of this kind of a new drug or vaccine. So we need to, our research setting should be as close as to the real environment where the problem is, where the research problem is. That is the idea. And also the same hypothesis can be tested in different settings. Let me take a small example. If you really want to see whether smoking causes lung cancer, if you want to see, the hypothesis is that smoking causes lung cancer. If this hypothesis is true, and that, just imagine if we take a petri dish and we add lung parenchymal tissues into that petri dish, and we culture the lung parenchymal cells, and we add nicotine or extract from smoke or nicotine perhaps to those cells. And we observe those cell lines for several days, perhaps. And if we observe any mutation or changes in the cells, and that is indicative of nicotine stimulating cancer in living cells or lung cells. So you see the setting happens in a lab, in petri dishes. But the problem is in patients, in people, in lungs, in living people. So that setting is quite distant. But even with a distant setting, we can do a research that can test the original hypothesis. What is the original hypothesis? That is smoking causing lung cancer. But now we tested, because those researchers could do it only in laboratory. They tested in laboratory, and they're trying to generalize it to people. And maybe we can do it on animals, in animal model. Like we can take one group of animal, or rats maybe, and another group of rats, and we expose one group of rats to smoke, and the other group we don't intervene. They are just there. One group is intervention, and they are exposed to smoke for several months, and then we examine their lungs for 3 months or 6 months, and we observe for development of cancers in rats. You see, we are again testing the same hypothesis, that is smoking causes lung cancer. Whether smoking causes lung cancer, the research question. Now the same research question is tested on animal model. So, and Now, if it is a clinician, I mean, they also can do the same research. Now they get patients with lung cancer, and those doctors who are taking care of those patients, they can ask, they can separate out patients with the history of smoking, They are without history of smoking. They don't smoke, and they can calculate the probability. And if they see a higher probability with patients with history of smoking, they can conclude that smoking causes lung cancer. Now, what is the setting of that research? It is a clinical research. At the same time, an epidemiologist who are not working with patients can also test the same hypothesis. For example, they can select an area in the country. They can separate out people who smoke and people who do not smoke. And they can continue to observe this group for 10 years or 15 years and calculate the percentage of people who develop cancers in the smoking group, and maybe it is little bigger, and the percentage of people who develop cancers in the non-smoking, do not smoke, non-smoking group. And that will solve the problem. You see, that research happened in the community. The researchers did not intervene, and it's a community-based research. So please understand that many research hypotheses can be tested in many settings. It depends on the setting, depends on the interest of the researcher, capacity of the researcher, the license available. For example, if you're not a doctor, you can't examine patients, so you can't do a clinical research. So if you are a veterinary experienced person, or if you are serving in a veterinary laboratory, you can easily do a research with animals. So likewise, it depends on your availability of facilities, your experience, expertise, and qualification will decide the research setting. But one general fact is that as far as the setting is close to the real setting, the findings are more reliable. We can rely on those findings because findings are closer to the truth. That is the idea. So it was about setting and the time. We just talked about time and statistical model. And I just mentioned about statistical model as well. So it is very important that for you to do research, good research, you have to have a good idea about, or at least an acceptable idea about statistics as well. Because statistics get involved during planning. You see, I mean, all these study planning, statistics is sampling, sample size calculation, and doing selecting measurements, selecting best measurements, all these involves statistics. So study planning involves statistics. And then later on, data analysis and interpretations involve statistics. Here, execution is the measurement period where you make measurements in the laboratory or in whatever the intended setting. These measurements will be used in statistical model again. So statistician should get involved from the beginning up to the end of the research. Otherwise, I mean, if you meet a statistician only at the end, probably your design is wrong, or probably your measurements are wrong. Probably you have not collected what you should have collected. All these problems could arise at the end. For example, many people have come to me to get their data analyzed, and when they come to me to get their data analyzed only, they realize how wrong their research design has been, or the fact that they have not measured what they should have measured, or the fact that they haven't had adequate sample size. Or likewise, all these problems can crop up later on. So that it is important either you are good in statistics or you consult a statistician at the time of study design. That is, inductive thinking generate hypothesis, deductive thinking design the research. At the designing stage, you need this statistical input to come up with a good statistical design. So if you make any mistakes in the designing stage, at this stage, a statistician cannot correct those things. Even you might meet the best statistician in the world, he cannot help you very much if you have made mistakes at the designing stage. That's the idea that you need to take. So software is not a big deal. What you need to have is some fundamental conceptual idea about statistical analysis. Any software is a good software. I mean, there are many softwares. SAS is there, SPSS is there, Minitab is there, some free softwares are there. R is a good open source software, and all these are really, really good and will do the job. But what we need to know what to do, how to use it. And different types of measurements, you need to have a good idea, like the scales of measurement, whether the scale that you are going to use in selecting your, in making your measurement is appropriate. Again, I'm not going to go into detail in relation to this, whether it is a nominal measurement or an ordinal measurement or interval or ratio measurement. For example, if you measure something, if you group something yes or no, it will be a nominal scale. Or male and female, it's a nominal scale. Or like if you categorize students as first year students, second year students, third year, fourth year, is again a nominal. Or it can be an ordinal as well, because there's an order: first year, second year, third year, fourth year. So that's an ordinal scale as well. Interval scale is where there are interval, like 1 centimeter to second centimeter to third centimeter. There are intervals. So measuring something length in centimeters or inches or meters is an interval scale. Ratio scale is a scale where there is an absolute zero. Like, measuring temperature on Kelvin scale has a zero Kelvin, absolute no temperature. But if you say 0 centigrade, it's not 0 temperature, right? It's different. So it is not a ratio scale. So ratio scale is where where the scale has an absolute zero value. So absolute zero means 0 on Kelvin scale means no temperature. That's the idea. But 0 on Celsius scale doesn't say that there's no temperature. Okay. So there are some ratio scales. I mean, 0 on inches is no length. 0 on centimeter is a ratio scale, no length. 0 in milligram means no weight. So those are ratio scales. This a little bit about accuracy and precision in relation to measurement. I mean, whatever you measure, the measurement should be accurate and at the same time should be precise. These are two things. Accuracy means it speaks for the truth. Precision means it measures it in the same way, same degree, same precision at the same time. Now look at these scenarios of hitting a dartboard. Now your target, when you start playing, your target is to hit the center. And if you hit the center every time, or most of the time, you are correct. You are correct. At the same time, you are hitting the center every time. So you are precise as well. You are hitting the same place every time. You are precise. You are capable of hitting the same place every time. So look at the situation B, scenario B. You have been hitting at the same place, hitting the same place at the same time, every time. So you have been precise, but have you been accurate? Are you correct? No, you are not correct. You are away from the center. You are inaccurate but precise. Now it is possible. Now, if you want to measure weight of something, just imagine the measuring device that you use. Every time, inflate the weight by 5 grams. Now, when the real weight is 20 grams, it measures as 25 grams. When the real weight is 10 grams, it measures as 15 grams. When the real weight is 30, it measures as 35. So you look at this measuring scale device. It is precise, but is it correct? It is not accurate. So that is why this precision and accuracy are two things. So we have to make sure that all our measurements are precise as well as accurate. Now, if you look at this situation, it's not precise at all. Now, this device, at times it inflates by 5 grams. The other time it deflates by 5 grams or 2 grams. So it varies a lot. Variability of that error of that variability is very high of that. So it is not a less precise device. So when you want to measure something, we need to worry about the precision of device as well as the accuracy of device as well. Now, if you look at this situation, although it is not precise, when you sum it up, when you sum everything, average will come into the one location. So average will be precise, but actually in general it is not precise, or it is not accurate as well because it is away from the center. Even average is away from the center. So it is not correct. So what we really want to have is try your best to maintain this situation. All your measurements are always accurate and precise. And so in relation to the function of research, as I said before, our finding of our research, finding of the study should be as close as to the truth in the nature, truth in the environment, truth in the problem. So that we should be able to generalize. That is what we need to do. But look at this situation. Now we have the truth in the nature. We have the truth in the nature here. Now to identify that, we have a research question. Based on the research question, we have a study plan, design. We deductively design the study. And that study, now that this study design, this is the protocol now design. This is the protocol. Now I give that protocol to my research assistant to implement. That is the real study. Now this is the real problem in the nature. So I inductively got my hypothesis here. That is research question or the hypothesis. And based on hypothesis, if this hypothesis is true, I made the prediction and deductively designed the experiment. Design experiment has a protocol. Protocol is how to execute it. That's the idea. Protocol is how step-by-step way of, when you write the total experiment in a step-by-step manner, that is the design experiment. When it is written in a step-by-step manner, in a chronological order, in relation to the time, that is a protocol, experimental protocol. And I give the protocol for my research assistant to do the real research. RA is doing it. So that is the actual study. My actual design is in my head. This is my actual study plan. And this is the truth in that study plan. If I do the study in this way, I will get this truth in my study. But my research assistant is doing it now. So that person will find something in the study, right? And that is the real result of the study. Now you see these 2-3 stages. If it is not clear to anybody, I will repeat it again because it's very important to understand. Now I decide my hypothesis. My reality is the girls are more intelligent than boys, right? My reality is now girls are more intelligent than boys. That is, I want to know whether this is there in the reality, in the nature, whether girls are more intelligent than boys now. I plan the study. Now use the IQ measuring device called X. IQ measuring device called Z. Okay, use the IQ measuring device called Z and take 2 representative samples of girls and boys and measure their IQ, calculate, and this is my study plan. So this is my written protocol now. I give this to be implemented by my RA. RA is doing it. So this is you understand the difference. This is only on paper. This is only on paper. I have written it. It's the way I have designed it now. And I give it to my RA to implement. RA is doing it. RA is doing it. So although I ask, for example, although I ask RA to use the questionnaire tool called Z, by mistake, RA do not use that tool called Z. RA use the tool called P. It is also similar. Maybe RA find R is Z. RA do not find the real Z tool. RA find a unvalidated version that I can call it Z1, unvalidated version. So then RA conduct the study. My question is whether RA will find the real truth I wanted to have in my study. Will the RA find that real truth? No. RA will find different finding actually. RA will find a different finding. The RA's finding is actually far away from my finding now, my intended finding. I wanted to find the real truth here, truth in my design study, but RA find the truth as he has done the study. Because RA has made a mistake. My RA has deviated from my study plan. So that lead to an error. And that reduces the validity of the research. And that is called internal validity. Now the internal validity is lost. So I have designed a very careful research, but in implementation, it has gone wrong. So the internal validity of the research is lost. You understand? But look at the other way. Now, when I design, I myself design to use not Z1. Because of my ignorance or my lack of awareness, I fail to realize that Z and Z1 are two different tools. So erroneously, because of my less understanding or ignorance, even in my planning stage itself, I decide to use Z1, not Z. The ideal would have been Z. So in my designing itself, you see, I have made an error so that I will not really capture the real problem in the nature. So that problem is in my designing. So in my designing, I make a decision, a wrong decision, that will take my study away from reality. So that is called, I'm losing an external validity of the research. So if I do a design error, that will, you will find, your design itself is faulty. Your research design itself is faulty. So that when you give this protocol, your RA will no problem. Okay, RA will use Z1 as I have instructed, will conduct the research. So there is no internal validity, loss of internal validity, because RA is doing the way I had asked him to do. So internal validity, no problem. But as there is an external validity issue, the research that is done by RA is again far from the truth. But why now there is an error? Because my design error. I have lost already the external validity. My design research is not close to the truth. Here, in the loss of internal validity, maybe my design research is really close to the truth, but RA, or when I am doing it, I make a mistake. I intend to take a sample in another way, but RA take a sample in a different way. So again, a loss of internal validity. So I think to keep it simple, I can put it like this. If there is an extra design error, you lose external validity. If there is an implementation error, you lose internal validity. Either way, you lose your ability to generalize your findings. So ideally, we should be avoiding both these errors. And at times, you might lose both external validity and internal validity. Then your real research will be really, really far away from the truth, and you will never find the truth in the nature. Truth in the problem, you will not find. So I think this is something that you need to keep in your mind. So taking a little bit time, the remaining about 10-15 minutes, just to speak about the kind of role that you really, I intend you to play, right? In research. Actually, if I recall my experience in other countries, Japan and other US or even other countries, we really, in those universities, we have less number of people called these technical officers or this category, to be honest. Actually, most of them are research assistant all research students. They are learning for a higher degree. At the same time, they are providing the technical assistance as well. So one day they will graduate as a PhD holder, and at that time, the institution will find new people as research assistant. So that's actually the arrangement that they have. So later they will become academics, they will become researchers, and they will develop on their own. So we rarely find a group of people who stay there as technical officers. So it's very, very less such people. I think so. My motivation is that so many things that I talk to you today, you will not go into that detail. Now, if you are not the person who is really designing the research. Now, I told you the most important part is inductively arriving at hypothesis and deductively designing the experiment. So this is hypothesis generation, this is design, and this is the execution, implementation. So if you are the person who is just implementing what is designed by someone else, you will not be a researcher. You will not be a researcher. And you will not really understand what is really going on as well. You will only do, okay, if your professor or somebody asks you to make some measurements, you will just make those measurements. You might not even know why you are measuring, and what would be the errors that you can make, what should be the real phenomenon that you should be capturing. You will not worry about this, and you will not even know. So you should play at this level. Then only, or you should try your best to play at this level. Then only actually you can call yourself a researcher. So at least at this level, I think the main duties that you can perform is something called, in any research. Now, just imagine now your professor has designed it. This part has been done. Your role is here. But still, you need to do a very detailed operational manual based on the protocol. That you execute the research, you implement the protocol in the same way without making a mistake in relation to each and every research participant. You can't make a mistake. So in that case, you need to have a very detailed operational manual more than the protocol. For example, protocol might say, okay, take 5 milligram of glucose. Protocol might say only that. But how to take 5 milligram of glucose, you need to know. So that details you need to develop. And a manual with such details around the protocol is called operational manual. Now, for example, at one stage when you are working with patients or a participant, you need a piece of cotton. So you need to keep it written. You need a piece of cotton that you will not make a mistake. So in the tray, when you start with a patient or a subject, so all these items, you need to have a list of items prepared in the operational manual. Okay, these items should be in the tray. So that when the patient is there, when the research participant is there, you will not jump up and down and you will not make a mistake. All items are there. So I think one important duty that you need to play is that maintaining that operational manual and preparing. It is you. I mean, your supervisor or the senior researcher will not prepare it for you. You will have to prepare it. And keeping everything documented. Keeping everything documented is a part that you can really pay. For example, if you are now doing research now, and after 1 year, there is another research student coming to work with you to do a similar research. And then you should be in a capacity to tell that person, new student, no. Now this is how we did it in the previous student. I mean, this is how I have documented. I have kept these things written, and see whether what you are doing is right or not. At least you should be able to question it and get the person to do the right thing. But if you do not document what you do, you will never ever will be able to do that. You will just be doing whatever you are asked to do. I think you should change that position. And the technical assistance that you need to provide. That means you need to be good at what you are doing in relation to your discipline, all your technical details. I think that is a basic thing, that the basic requirement, right? That is a very basic requirement. If you are not competent with your devices, equipment, then you cannot be there. And the other thing, data management. I think you should be very good at Excel, how to do calculations, making formulas and all that with Excel. I think you should be very, very good at that. And also it should be excellent if you are good at handling statistical software and do data management at that level. I think that should be one of your aim. Learning statistics and learning a statistical software and start playing at that level. And these are some basic. And in relation to that, making your intellectual contribution. And now intellectual contribution happens in the first two phases. Intellectual contribution happen in the inductive thinking, deductive thinking, that is generating hypothesis and design. And also implementation, there is inductive thinking. This is the first, second, third stage. Why? Like, for example, with your experience, if you can tell your researcher, whoever, research student or researcher, okay, if you do it in this way, this will go wrong. If you rather than making this measurement, if you take this kind of measurement, you will get better results. Or, I mean, if you can say, okay, rather than selecting this measurement, if you measure it in this way, your measurements will be more precise or accurate. I mean, if you are in if you have that capacity to give that intellectual contribution, and then actually you are producing your brain input to that particular research, that is an intellectual contribution, a cognitive contribution. That is the minimum. So you should be, if you can suggest hypotheses and explain observation patterns. So if you are experienced in your field, you can do that, all right? And collection of relevant literature. If you can collect literature and study the area and help the researcher or the professor, I mean, definitely professor will, in 2-3 years time, definitely professor will ask you to do your own research and be the principal investigator. Principal investigator is the person who is generating the hypothesis and designing the experiment. That is the principal investigator mainly. And going through the literature, collecting literature, going through the literature and refining the protocols and providing constructive suggestions to your researcher or the supervisor or your professor. I mean, and ability to contribute by data analysis. That is a real intellectual contribution. If you can do data analysis, if you are good in statistics, I think you will be a wonderful person to your research team, and there will be a huge intellectual contribution from you to the research that is happening in your lab. And in addition, your mindset, I think your mindset should be to minimize errors. I mean, if you are with an attitude that, okay, the person asked me to do this measure, I'm just measuring it. I mean, you're not worried about accuracy or precision, you're just doing it. I think you will never be a good researcher. So your mindset will be whatever the measurement. I mean, you need to develop that trait, okay? Even at home, if you're making a small measurement for some work at home, some domestic work, you should try your best to make the best precise measurement as a technical officer or as a researcher. So that trait, gati lakshana, should be in you. Then only you can be a researcher. And you should be prepared to learn further. You should be prepared to learn further. You should be prepared to take a challenge. Learning research methodology, learning statistics, learning about your techniques, mastering your techniques, all this should happen. And also eager to find solutions to existing problems. For example, if you see that a researcher in your lab is experiencing a problem, I think you should be motivated enough and competent enough to find a solution for that person with your experience. Maybe he's just a research student or an MPhil student or a PhD student working with you. And you, with your experience, you should be able to suggest a solution for the problems that they are experiencing. So that your experience and your knowledge and your competency, all this matter. All this will matter. And your preparedness and how prepared you are. You should be ready to do additional reading. You should be ready to update yourself in relation to whatever you are doing. Now, if you are working in a particular area in your lab, and perhaps you should be the most updated person. And perhaps the professor must be asking you, okay, Did you find out any new development in relation to this technique or any device? Or if your professor or the researchers must ask you whether there are any updated or better devices to do this, you should be able to answer that. You should know all these. So you need to update yourself. So you should be good in software management, like simple software, Word, Excel. I think if not, you should be learning this. And you should be, as I told you before, you should be good, or you should try to be good in research methodology and statistics. When I say research methodology, it is the study about research. All what we discussed is research methodology. But if I say research methods, that means different tools and techniques that we are going to use. So there's a small difference in that. Research method. Now, research method that to solve one problem is different to research method that we use to solve another problem. But when I say research methodology, that is what we are learning today here. That is about research, learning about research, learning how to do research, learning how to do good research, learning how to make good measurements. All that is research methodology. And the other aspect is statistics. I really encourage you to be good in statistics if possible. To be honest, I have I just got this. Is there like these are two books that I have written. One on basic statistics and one on research methodology. To be honest, I never learned these things from anybody. I didn't go to classes, so I didn't. I started going to a class, but I could not continue it. But all these things that I am even teaching you today, I have self-learned. So if it is possible for me, it is possible for you as well. That is how I see it. So in that case, if you are prepared to do that, I think you can do that. And for that, you need to have some characteristics with you that you should be able to take the initiative. And you should be organized and efficient. Time management and your organizing, your abilities, you're getting things done. And you should be a dependable and relied upon person. I mean, you should behave in that way. For example, if your professor or another researcher request your help, and you should be dependable person and make sure that you are really doing it, you are really delivering it. And you should be a person who is eager to learn, right? All these things are very, very important. And also, I just thought of telling you something about who is an author and who is not an author in a research. And I find this complaint from many times in our system. And I know there's a grievance, like at times, perhaps you are worried that you are not identified as an author in particular research when you really help. So who is an author, who is not an author? So this is the criteria of International Committee of Medical Journal Editors. So they are based on this standard, and they identify one person as an author if that person has intellectually contributed to the work, not technically contributed. So it is very clear. For example, now when we write research papers, there are several areas I have to explain. For example, if I want to get Prasad as an author, I have to write to the journal. There's a separate in submission. I have to provide this information. I have to explain how Prasad helped in designing and conceiving the research question and designing the research. I have to explain how Prasad contributed in executing the research. I have to explain how Prasad contributed in analyzing and interpreting data. I have to explain how Prasad contributed in writing the manuscript, editing the manuscript, and whether the person agrees with the manuscript. You see, then only such a person is accepted as an author for a research article, research journal publication. So in that case, if you are not ready to contribute intellectually, actually it is difficult to, now based on these standards, it is difficult to expect to be an author. So I think I want to tell this to you. So please don't misunderstand. Please don't start fighting with your researchers or professors. Best thing, start playing at that level. Start contributing intellectually in these areas. Then automatically you will have your place, you will have your name, and you will have your credit, and you will get awards, you will get everything. So that is actually what I can. And now there are many technical officers at level. There are many people who are contributing at that level already, and they are getting credits as well. I know there are several people, they have even already completed their master's degrees and PhDs, and some are now good researchers, and some are now good academics, and some are now close to be even professors in Sri Lanka. Oh, there's at least one professor now already who has originally been a technical officer. So I think there's no end to your career development. So there's nobody is blocking it, nobody is preventing it. It is only you actually blocking yourself, or it is only you preventing yourself. There's no barrier for that today. Opportunities are immense, not like 40 years or 30 years or 20 years before. There are enough opportunities, there are enough place for you to upgrade yourself and for your career development. So with that small note, I think I can wind up this session. I wish you good luck to all of you. And I will share this display, the slideshow with your union. You can get a copy of it. I will share it as a PDF version. So thank you so much. And if there are any remaining questions at this point, you can probably post it on the chat box. So it seems there are no serious questions. In that instance, okay. So one person has asked whether what is the minimum number of sample size required for data analysis. There's no answer for that, because it depends on the research question. It depends on the research question, and depending on the research question, we need to calculate the sample size required to test that particular hypothesis. That is how we work. Now, even for sample size calculation, there are even free software. Good. I use one software called G-Power. I can write it here. G-Power. You can download it. It's available both for Mac and Windows. It's an excellent piece of software to calculate sample size, but you need to know how to use it. You need to know the meaning and how to use these different menus, etc. So, if we will do a research by our own, no matter in the field of engineering, management, or any other, how can we find the best publisher to publish that research paper? All right. Okay. I mean, it's a very simple thing. When you do a research, you are reading literature now. So then you will come across journal articles which are published, which publish research of that nature. So you will have to submit to one of those journals. That is the best. Right. If not, let us stop. Are there any other questions? I don't know. Right. So then with that note, let me stop here. And thank you so much for listening to me. I wish you all good luck. Oh.
I would like to thank Professor Anjit W. Palegama for giving us a valuable session. So now I would like to invite Mr. KPG Karunaratne, General Secretary, Sri Lanka University's Technical Officer Union, to deliver the token of appreciation. Please wait for a few minutes. Appreciation. Now, now we are going to end the session today. I would like to invite you all to attend tomorrow's session. So I hope you all join us tomorrow at 9 a.m. Thank you.